to my channel. I have already posted 2 videos on mole revision. That is chapter 1 of class 11th CBSE final exams. First part dealt with scientific notation, significant figures, units, and the second one dealt with the 5 laws of chemical combination. So today I'll be dealing with Dalton's atomic theory, followed by the main terms of mole concept, that is atomic masses, molecular masses, how to calculate number of atoms, molecules, moles, etc. So you generally find a problem with in dealing with these. So I'll try to make that clear in brief in the form of a quick shot. So I hope it helps. Stay geared, stay very consistent. Please keep learning every day. I hope this helps you for your final exams. So let us start. With Dalton's atomic theory, I just want to bring to your notice these few terms given on the first page of NCERT. This is the introductory part and very important as questions. So just remember the uses of these drugs: cisplatin and Taxol, used in cancer therapy; AZT, azidothymidine, for AIDS patients; refrigerants, some examples: CFCs, that is chlorofluorocarbons. These are compounds of chlorine, fluorine, and carbon. For example, CFCl3, then CF2Cl2, and these are responsible for ozone depletion, and some greenhouse gases like methane and carbon dioxide. You just have to learn these names for 1 mark question that may be asked. So next we move on to Dalton's atomic theory. The main postulates of Dalton's atomic theory as given in NCERT. These are: matter consists of indivisible particles called atoms. That is, according to Dalton's atomic theory, matter has the simplest particle as atom, which cannot be further divided into electrons, protons, and neutrons. The theories that came later suggested that an atom can be divided further, but according to Dalton, matter consists of indivisible particles called atoms. The second postulate says all the atoms of a given element have identical physical and chemical properties, but atoms of different elements differ in their properties. Third says compounds are formed when atoms of different elements combine in simple whole number ratios. So this was in accordance with law of definite proportions. Then the next point says chemical reactions involve reorganization of atoms, but atoms are neither created nor destroyed in chemical reactions. Now, reorganization of atoms means formation of molecules. And according to Dalton's theory, atoms are neither created nor destroyed in chemical reactions. So this particular point was in accordance with law of conservation of mass. Now, what are the limitations of Dalton's atomic theory? Could not explain Gay-Lussac's law of combining volumes, could not explain the existence of isotopes. What are isotopes? Isotopes are atoms of the same element having the same atomic number but different mass number. And according to Dalton's atomic theory, all atoms of the same element should be identical in all respects. Hence, existence of isotopes was a limitation to Dalton's atomic theory. Then existence of isobars. According to Dalton's atomic theory, atoms of different elements should be different in all respects. But if we take an example of potassium and calcium, these are atoms of different elements with different atomic number but same mass number. Hence, atoms of different elements can be identical in some respects, which was not explained by Dalton's atomic theory. Next is E is equal to mc square, the law of conservation of mass and energy, that is interconversion of mass and energy, which again was not commented upon by Dalton's atomic theory. Dalton's atomic theory could only justify the law of conservation of mass. Now, this theory could not explain the reason for combining atoms. It only explained to us that atoms combine to form molecules, but why do they combine to form molecules? This was not explained by Dalton's atomic theory. Now we come to the main points regarding mole concept. So for mole concept, we start with atomic masses. Atomic masses cannot be calculated in an absolute way. That means the actual mass of an atom cannot be calculated with complete accuracy. Why? because atoms are extremely small entities, very difficult to isolate a single atom of any species, of any element, and then to experimentally measure its actual atomic mass is very difficult. Hence, absolute atomic masses are not measured, whereas relative atomic masses are measured, and for that, a standard reference was to be chosen. The first chosen standard was hydrogen. Why chosen? Because it was the lightest element, but why discarded? Limitation of choosing hydrogen to find atomic masses was the results had large experimental error and the masses found were found to be fractional. So it was replaced by a chosen standard oxygen. Why chosen? Because it was most reactive. And then the present day standard chosen for atomic masses is the C12 isotope. Now, why is this a suitable reference? Because the results obtained by choosing this as a standard are more inferable. The fractional masses found were less, and with this chosen standard, there was a smaller experimental error. Now, how do we define atomic mass? Atomic mass of an element is the number of times an atom of an element is heavier than an atom of carbon taken as 12. It is the average relative mass of its atoms as compared to that of an atom of C12. Now, I have highlighted the words average and relative because this is a separate question asked: why average or why relative? Why do we use the terms average and why do we use relative? Relative because it is compared to C12, since it's a comparative mass, we use the term relative. Why average? Because it is expressed with respect to fractional abundance. What is fractional abundance? It is the ratio of number of atoms of each isotope with respect to total number of atoms of all isotopes. For example, if you're talking about chlorine 17 35 isotope and chlorine 17 37 isotope, these in nature have been found to be in the relative abundance of 3 is to 4, which means the fractional abundance of chlorine 35 isotope will be 3 by 4 and that of Cl37 will be 1 by 4. Or if I want to express it as a fraction, I write 0.75 and 0.25. And in case I want to express this as a percentage, then as a percentage, chlorine 35, I would say, is 75% and chlorine 37 is 25% because fractional abundance into 100 gives us abundance in percent. Let us look at the numericals that can be asked based on this. The first form of the numerical is two isotopes of chlorine 35 and chlorine 37 found in nature in abundance of 75% to 25%. Calculate average atomic mass of chlorine. So, what are we going to do in this case? 35 into 75 plus 37 into 25 divided by 100. Why have we done like this? Because chlorine 35 is present as 75%. So 35 into 75 plus 37 into 25, the abundance of this isotope, and divided by 100. What is 100? It is the sum total of these two percentages. When we solve this, we get the answer as 35.5. 35.5 is the average atomic mass of chlorine. We could have solved the same question by another way. 35 into 75% can also be quoted as 75 by 100, which is 0.75. That means I'm taking the fractional abundance. And 37 into 0.25. And 0.75 plus 0.25, that is sum total of the fractional abundance is 1. So again, I'm going to get the answer as 35.5. Or I could have chosen to solve it this way also. For 75% means out of every 4 atoms, 1 atom weighs 35. Sorry, 3 atoms weigh 35 and 1 weighs 37. and the total atoms are 4. So I get it as 35.5. So I could calculate it by any of these three methods. I hope this is well understood. So this is one way a question can be asked where you are given the atomic masses of the individual isotopes and their fractional abundance, and you are asked the average atomic mass. Now, second way in which this question can be asked is this time you've been given two isotopes of boron, boron 10 and boron 11. The average atomic mass is given, and they're asking you to calculate the percentage of abundance, right? So this time, what are we going to do? Let us assume boron 10 to be present as X%, and then boron 11 has to be present as 100 minus X. Why? Since we are talking about percentage, it means if one is X, the other will be 100 minus X, right? So 10 into X plus 11 into 100 minus X upon 100 should be equal to 10.8. That is the average mass that is given to us. So 10x plus 1100 minus 11x is equal to 10.8 into 100. This will come out to be x is equal to 1100 minus 1080, which means x is equal to 20%. So therefore, our answer will be x, that is percentage of boron 10 is going to be 20%, and that of boron 11 will therefore be 100 minus 20, that is 80%. So in this numerical, the average atomic mass was given. We were to calculate the percentages. But in the previous question of chlorine, we were given the average, the percentages, and we were to calculate the average. So these are the two kinds of questions that can be asked related to isotopes. Next, we come to atomic mass. Atomic masses are measured with mass spectrometer. Again, this is a line given in NCERT. You must know the actual mass of an atom is calculated using a mass spectrometer. And then using a mass spectrometer, mass of one atom of carbon 12 isotope was found to be equal to these many grams. So 1 mole of carbon weighs 12 gram. Number of atoms in 12 gram could be calculated as 12 is the mass of 1 mole of atoms. This is the mass of one atom. Okay, we decided mole to be equal to the gram atomic mass quantity. So 1 mole was considered to be the number of atoms present in 12 grams of carbon. So 12 gram was divided by mass of each atom of carbon, which was measured experimentally using a mass spectrometer, and we obtained this number, which suggested these many atoms of C12 are present in 12 gram of this isotope. And this number was fixed as Avogadro number. And we decided, based on this observation, that 1 mole of any substance, of every substance, be it an atom or a molecule or an ion, will contain equal to these many entities. These many entities means if I'm talking about 1 mole of atoms, it will have these many atoms. 1 mole of molecules will have these many molecules, and so on. We are going to elaborate this ahead. Now, further, since atomic masses are very, very small in magnitude, hence a smaller unit was required to express atomic masses. So, based on the C12 isotope, the scale that was chosen to describe atomic masses was called atomic mass unit scale, the AMU scale, which is called as the unified scale in the present form. The unified scale. On this scale, mass of one atom of C12 is 12 AMU, or these days called as 12U. And 1U is equal to reciprocal of Avogadro number, that is 1.6605 into 10 to the power minus 24 gram. Hence, if mass of one atom is equal to 1.99 into 10 to the power minus 23 grams, as we calculated here experimentally, if mass of one atom of C12 is equal to these many, then mass of Avogadro number of atoms is going to be this number multiplied by Avogadro number, which is going to come out to be 12. Fine, you should know all these relations, children. Any of these relations can be asked from you. I repeat, what is the summary of this page? One atom of C12 weighs these many grams. This was measured with a mass spectrometer. 1 mole of carbon weighs 12 grams. So 12 gram is the total mass of 1 mole. Each atom is weighing this much. So 1 mole of C12 will have these many atoms. This was considered to be Avogadro number. Then 1 AMU was defined as a quantity of matter equal to 1/12 of the mass of an atom of C12 isotope, which means one atom of C12 is 12U and 1 mole of atoms of C12, that is Avogadro number of atoms of C12 will weigh 12 gram. This magnitude is always the same. One atom, we measure this atomic mass in U, and this is the mass of 1 mole. It's the same number, same magnitude, but expressed in gram. Please remember this, right? Then, if I relate here, 1U is 1/12 of the mass of one atom of C12. What is the mass of one atom of C12 in gram? How can we calculate that? How can we calculate that? We know Avogadro number of atoms. We just discussed this. Avogadro number of atoms of C12 weigh 12 gram. Or in other words, I can say 6.02 into 10 to the power 23 atoms of C12 weigh 12 gram. So one single atom is going to weigh 12 upon Avogadro number of grams. This is the weight of one atom. Okay, so 1U is equal to 1/12 of the mass of one atom of C12. So if I substitute the mass of one atom of C12 in gram, I'm going to substitute this. So 1U comes out to be equal to this cancels off. 1U comes out to be 1 upon Avogadro number of gram. 1U is 1 by Avogadro number gram, which on calculating comes out to be 1.6605 into 10 to the power minus 24 gram. You have to learn this outcome. This outcome you have to learn. 1U is nothing but reciprocal of Avogadro's number, which is also equal to 1.6605 into 10 to the power minus 24 gram. You can just reverse, replay this and learn these concepts, children. Very important. Also visualize one molecule of water in the same way is going to weigh 18U. One single molecule. This is one single molecule. This is hydrogen, oxygen, and oxygen. One single molecule weighs, this is oxygen, hydrogen, hydrogen. This is one single molecule of water weighing 18U. And this glass of water, let us say this weighs 18 gram. This has 1 mole of water molecules, means this has 6.00 into 10 to the power 23 molecules of water, which will together weigh 18 gram. So if we derive this one molecule, please learn this, understand this. You can redo, replay because children are often confused with this. One molecule of water weighs 18 U, right? If I ask you what is the mass of one molecule of water in gram, then we discussed 1 U is 1 upon Avogadro number of grams. So I will do 18 into 1 upon Avogadro number of gram. This is the mass of one molecule in gram. This was the mass of one molecule in U. Please remember, it's one molecule. In U is 18U, but in gram is 18 upon Avogadro number. And 1 mole of molecules, which is also equal to Avogadro number of molecules in gram, should weigh how much? 18 into 1 upon Avogadro number is the mass of one molecule. This is the mass of one molecule. I want the mass of Avogadro number of molecules. I'm going to multiply this with Avogadro number. This cancels off. I am left with 18 grams. So 1 mole molecules. This is a big number. 6.02 into 10 to the power 23 molecules, children, together weigh 18 grams. Okay, just for you to visualize, I'm just giving you an example. Fine. If I give you an example to visualize, a cricket ball. Let us say, okay, just imagine a tennis ball. Okay, tennis ball or maybe a cricket ball. These are going to weigh somewhere about 10 gram to 50 gram, roughly. You can just to visualize. One ring that you're wearing weighs approximately 10 gram. The bangle or the kada that you wear, yeah, that is approximately 20 gram. Fine. So do you think one molecule of water can weigh something like 18 gram? No. We have so many molecules of oxygen, water vapor, nitrogen around us in the air. So can you visualize such big molecules hitting us every minute? Just visualize whenever you feel like answering the mass of one molecule is 18 gram. Just visualize this concept. Okay, one molecule has a very, very small mass. So it's 18U or 18 upon Avogadro number gram. But one mole molecule, which is a big number, these many molecules together are going to weigh 18 gram. I hope this concept is very clear with you. Okay, so one atom weighs equal to atomic mass in U. One molecule weighs molecular weight in U. But one mole of atoms, which we also called gram atoms. Gram atoms means one mole of atoms. This is equal to gram atomic mass, that is atomic weight in gram. And one mole of molecules, that is Avogadro number of molecules. We also call it as gram mole or gram molecule. This is equal to gram molecular weight, that is molecular weight in gram. Now, if we just take up some examples, supposing I ask you mass of one molecule of oxygen, you're going to say 32U, right? Or 32 upon Avogadro number of grams. Why? Because we know 1U is 1 upon Avogadro number of grams. Clear? In other words, you can also memorize, you can also remember, children, it as that mass of one atom in gram is also equal to its gram atomic mass upon Avogadro number. Gram atomic mass upon Avogadro number. So many different ways I've explained this concept to you, right? 1 mole of oxygen molecule is going to be 32 gram. I hope this is clear. In case it is not, just replay it and just fix it into your memory, children. It's very important. Okay, repetitively doing something is going to make you good in that. So similarly, if I ask you mass of one molecule of water, you're going to say this is 18U, or if I want the answer in gram, you will say it's 18 upon Avogadro number of grams. Mass of 1 mole of water molecules, 1 mole of molecules is going to be 18 gram. And if I ask you 1 molecule of water contains dash mass of hydrogen, what are you going to say? You will say 2U. But if my question to you is 1 mole of water molecules, 1 mole of water molecules contain dash mass of hydrogen. Obviously, now you're going to say 2 gram, right? Similarly, if instead of hydrogen, I had asked you about oxygen, if I had asked you about oxygen, what would you say? Here you would say 16U, and here you would say 16 gram. Clear? Similarly, if I had asked you 1 molecule of water contains how many atoms of different kinds, you would say 2 atoms of hydrogen and 1 atom of oxygen. Very simple and understandable. But if I ask you 1 mole of water molecules contain how many atoms? Now you would say 2 moles of atoms of hydrogen. 2 moles means 2 into Avogadro number of atoms, and 2 moles of hydrogen atoms can also be written as 2 gram atoms of hydrogen plus 1 into Avogadro number of atoms of oxygen, or 1 mole of oxygen atoms. It's very important to understand we're talking about moles of atoms or moles of molecules. And here also 1 gram atom of oxygen. 1 mole of water molecule contains 2 gram atoms of hydrogen, means 2 moles of hydrogen atoms, means 2 into Avogadro number of atoms of hydrogen. And 1 gram atom of oxygen means 1 mole or Avogadro number of oxygen atoms. So I hope this concept is very clear to you. Now, coming to 1 mole of a substance always contains Avogadro number of particles, which could be atoms, molecules, ions, electrons, neutrons, anything, depending on what we are talking of. Right? So number of entities in 1 mole is always called Avogadro number. Then you can be asked a question, what is the unit of Avogadro number? The unit of Avogadro number is mole inverse per mole. Please remember this. The unit of Avogadro number is mole inverse or per mole. Right? So the mass of 1 mole of a substance expressed in gram is called gram molar mass. I've already explained this to you. And for atoms, this is called gram atomic mass. For molecules, gram molar mass. And for ionic compound, it's called gram formula mass. For example, if I ask you what is the gram atomic mass of chlorine, you would say 35.5 gram. If I ask you what is the gram molecular mass of carbon dioxide? You're going to calculate it as 12 plus 2 into 16, and you would say 44 gram. If I ask you what is the gram formula mass for sodium chloride is an ionic compound, and ionic compounds don't exist as molecules, so we use the word formula mass, formulas. So it's calculated like molecular mass only, but we use a different term, that is formula mass for this. So 23 is the atomic mass of sodium, 35.5 for chlorine. This comes out to be 58.5 gram. So Avogadro's number as a unit conversion factor. In the last previous video, we had learned what is unit conversion factor. So how is Avogadro number as a conversion factor? We know 1 mole is equal to 6.02 into 10 to the power 23 particles. So 6.023 upon 1 mole or 1 mole upon 6.02 into 10 to the power 23. Each of these is a unit conversion factor. Okay, the particle can be anything. It can be an atom, a molecule, it can be an electron, a neutron, a proton, ions, anything. For example, if I ask you 1 mole of nitride ions contain how many ions? You would say 6.02 into 10 to the power 23 ions. If I ask you 1 mole of electrons means how many electrons? 6.02 into 10 to the power 23 electrons. And similarly, any species can be expressed this way. Next, we come to what is the molar mass of water? Molar mass. Molar mass means mass of 1 mole, that is 18 gram. But what is the molecular mass of water? It is the mass of 1 molecule. It is 18.02 U. And molar mass is also gram molecular weight, and molecular mass is just molecular mass. Fine. Molecular mass is the mass of one molecule. Okay. Then we've already discussed this. 1 U is equal to 1 upon Avogadro number. What is the molar mass of sodium chloride? This is also called as the formula mass. Why? Because sodium chloride is an ionic compound. So here molar mass will also be called as formula mass. So what is the formula mass for sodium chloride? It is 58.5. This is gram formula mass, 58.5 gram. And formula mass of sodium chloride, that is mass of just one formula, is going to be for the same reason, 58.5 U. Right? Just one sodium and one chlorine. Okay. So now, how do we do the interconversions? How do we interconvert the quantity mole to different concepts, to number, to mass, and to volume? How do we do that? The formulas that we're going to use, children, just try and understand the formulas we're going to use. Just remember, if I want to calculate, I want to convert a given weight or a given number or a given volume to number of moles. I want to calculate number of moles in a given weight of a compound. I'm going to divide it by gram molecular weight. If it's an element, I'll be dividing it with gram atomic weight. If I want to calculate number of moles, when number of atoms is given to me, I'm going to divide it with Avogadro number. So n, whenever you have to calculate number of moles, what you do is you divide whatever quantity is given by the molar quantity in the same unit. Like, for example, if mass in gram is given and you want to convert it to moles, you'll divide it by gram molecular mass. If number of molecules are given, you divide it with Avogadro number. And if volume in ml is given, you divide it by 22.22700 ml. This is the value of molar volume at the new STP, which is 1 bar and 273 Kelvin. And in case volume was given in liter, then you will divide it with 22.7 liter. Right? So I've made a flow chart here. This suggests 1 mole you need to convert. See, the formula is number of moles is equal to given weight upon gram molecular weight, number of molecules upon Avogadro number, or volume in ml upon 22700. Right? So which means if I want to convert moles to mass, what do I do? Moles to mass. Right? So W is going to be number of moles into gram molecular mass. So I'm going to multiply number of moles with gram molecular mass to get mass. Similarly, if I want to know number of molecules, I'm going to multiply number of moles with Avogadro number. Molecules is number of moles into Avogadro number is going to give me number of molecules. If I want to calculate volume, what do I do? N is equal to V upon 22700. So I'm going to multiply N with 22.7 liter if this is in liter, and if this is in ml, then N into 22700. This is what this flow chart is telling us. Okay. And supposing volume is known and you want to convert it to this, then you divide it by 22.7. Okay. If volume is known, you want to convert it to moles, divide volume by 22.7 or 22700, you will get number of moles. So this is what this flow chart is explaining. Now, this is going back, right? Volume to moles, divide by 22.7. This is mass 2 moles divided by atomic weight or molecular weight, and this is number to moles divided with Avogadro number. As an example, if I ask you calculate number of moles in, let us say, 3.2 gram of oxygen gas. So what am I going to do? According to the formula, number of moles is given weight upon gram molecular weight. So I'm going to do 3.2 upon 32. Similarly, if I ask you number of moles in 2.27 liter of ammonia gas at STP. Remember, we can use the number 22.7 only for volume at STP. Given volume divided by 22.7, this is going to give me number of moles from volume. So what are we going to do? If mass is known and I want to convert it to moles, I'm dividing it with gram molecular weight. If volume is known and I want to convert it to moles, I'm going to divide it by 22.7. I hope this application is clear to all. So we move on to the next one. I've already explained this concept to you. This is approximately, this 1 bar is approximately equal to 760 mm of mercury or 76 centimeter. The older standard condition of pressure used to be 1 atmosphere, which was equal to 760 mm of mercury or 76 centimeter of mercury, right? But the new standard is 1 bar. Okay. So 1 mole of hydrogen gas has a volume of 22.7 decimeter cube, which is equal to 1 liter at NTP. Now, 1 decimeter cube is equal to 1 liter. I have explained this in the first video. So 3 moles of nitrogen gas means, what do? I want the volume of 3 mole of nitrogen gas at STP. How do I calculate? 1 mole occupies 22.7 liter or decimeter cube. So 3 mole is going to occupy 22.7 into 3, which is going to be this value. So similarly, you want to calculate for 0.5 mole, so it's going to be half. So this is what I have already discussed. This is for number of particles, this is for mass, and this is for volume, right? So this is what I have just discussed in detail with you all. This is just an overview. Now, what is the learning check? The learning check here is mass and mass number relationship. So let us just solve this. Number of atoms in 0.5 mole of aluminium. So you know number of moles is equal to number upon Avogadro number. Therefore, this time we know 0.5 mole. We need to know number of atoms and we are going to divide it with Avogadro number. So just solve it. N is going to be equal to 0.5 into 6.02 into 10 to the power 23, which is going to be approximately 3.01 into 10 to the power 23 atoms. So the answer for this part is going to be 3.01 into 10 to the power 23. The next question is number of moles of sulfur in these many sulfur atoms. So this time again, number of moles is equal to N upon Avogadro number. And this time we have to find out number of moles. So this is the given number of atoms and you're going to divide it with Avogadro number. So solve it and you get the answer. Mass of 0.5 mole of aluminium atoms. So we are talking about mass now. Number of moles is equal to given mass upon gram atomic mass. Why atomic mass? Because we are talking about an element. If this was a molecule, I would have written here gram molecular mass. So number of moles is 0.5. I want mass. Gram atomic mass of aluminium is 27. So solve this and you get W in gram. Mass of one atom of aluminium. And what is mass of one atom of aluminium? It is equal to either 27U or 27 upon Avogadro number of grams, because we did mass of one atom is its gram atomic mass divided by Avogadro number if we want the answer in gram, and if we want the answer in U, it's atomic weight in U. What is mass of Avogadro number of atoms of aluminium? It's equal to the gram atomic mass, which is going to be equal to 27 gram. So here I have a homework question for you. Number of gram atoms in 1 mole of alumina. I'll be sharing this answer in the next video. The next question is to check your concepts about mass volume relationship. You can just pause and solve the answers on your own and then check the answers, then compare the answers. Volume of 0.5 mole of water vapor. So now we are using mole in terms of volume. So it's going to be this formula, which means 0.5 into 22.7. This is going to give me volume in liter. Volume of steam. Steam means chemically water, water vapor, containing these many molecules. So it's a relation between volume and number of molecules. What am I going to do? I know N is equal to V upon 22.7. This is in liter, or it is equal to N upon Avogadro number. Clear? So in these, we know this, we know this, and we know this, and we've been asked this. So what are we going to do? We are going to use this relation. So V liter is going to be equal to 1.8 into 10 to the power 24. I've substituted this for N upon Avogadro number into 22.7. So this is this, Avogadro number is this, and 22.7 I've taken into, and I'll be getting V liter. Solve it and you get your answer. The next one says mass of 2.27 liter. This is the relation between mass and volume. Again, I take up N is equal to given weight upon gram molecular weight is equal to V liter upon 22.7. So this time we are going to use this. Why? We know we need to calculate W. We know volume in liter. We know 22.7. And we know the gram molecular mass of water as 18. Solve this and you get your answer as 1.8 gram. Okay. And then next is mass of 1 liter of water vapor. Water vapor at STP. So what is mass of 1 liter of water vapor at STP? Again the same. Given mass upon gram molecular mass is equal to V liter upon 22.7. So W is what I need. This is 1 liter. This is 22.7 into gram molecular mass is 18. Fine. And here I would like to mention, supposing children, I had asked you here, mass of 1 liter of liquid water. Remember, STP condition is only for gases. Okay, and this 22.7 liter volume is for 1 mole of a gas at STP. It is not applicable to liquids. So if mass of 1 liter of liquid water is asked, what are you going to do? Now you're going to use the concept density of water is 1 gram per cc. Density of water is 1 gram per cc or 1 gram per ml, which means 1 ml water is going to weigh 1 gram. So 1 liter means 1000 ml is going to weigh 1000 gram or 1 kg. So what will be the answer to this question? To this question, the answer will be 1 kg. I hope this is clear. So next is total atoms required to make 22.7 liter of water at STP. Remember, total atoms I'm asking. So solve this and answer will be shared in the next video.